Thank the organizers for making me the chair. This is a conventional statement. And we have the second day of the program of TAP, which is sort of very interesting. I'm going to start with Jim Libby, the first one, 45 minutes. And the organizers have been very careful in making the talks not to go beyond 45 minutes. And I was reminded of Dada Biswas used to tell, no seminar should go beyond 1 hour. That's because at my old age, I can't sleep for more than 1 hour at this. So it's only 45 minutes. We will all be awake. Thank you. Jim Libby, your talk.
Yes. Well, I hope you enjoy your 45-minute nap initially. And also, this is a talk on flavour physics, but the flavour of breakfast seems to have won. So I will give you a brief tour of Belle II physics. I'll start with the why, explain why we're doing flavour physics in E plus E minus collisions, and particularly what Belle II is. And then I'll give some highlights. Initially, I will talk a little bit about the general methods that we use at Belle II. And then I'll talk about several B physics measurements, which are really the bread and butter measurements of Belle II. And then I'll talk a little bit more about things that are not B physics, and this is becoming ever more important at Belle II. So this is some tau physics, some measurements related to the G-2 muon anomaly, and inspired by something said yesterday, I'll say something about exotic hadrons before describing the current status and the plans. So the why. Flavour physics has a very important role in the development of the standard model in general. And an example of this is early on, of course, there was this particle zoo discovered in the 50s and 60s, and then it was sort of made sense of by the eightfold way and the introduction of 3 quarks. However, there were still some unusual things happening. For example, for the long-lived neutral kaon, it was expected that it should be able to decay into 2 muons. And there were lots of theories about why this was possible and the rate it should happen. However, it was not seen. It was expected that it would be observed at some rate. Now, on the right side, we have our modern view of this in terms of a Feynman diagram, and it's a flavor-changing neutral current decay that only happens at second order in the weak interaction. And here it's written in terms of just those 3 light quarks. And this is how it would proceed. But the answer came because of the so-called Jim mechanism that predicted that there should be a 4th quark. So this is well before any observation of the charm quark. It was suggested that there should be one. And this would then lead to the suppression of such flavor-changing neutral currents. So using Cabibbo's quark mixing mechanism, you get the second diagram down here, which has the charm quark, but you pick up a minus sign from the quark mixing, and that leads to an almost perfect cancellation between these 2 diagrams. The only difference is the mass difference between the up quark and the charm quark. So what's interesting about this in the whole story of flavor physics is you're actually looking at a particle which has got a mass which is significantly less than the charm quark mass, except you're learning something about a higher mass scale. And that's generally the story in flavor physics, that you're always learning about higher mass scales by looking at lower energy phenomena. So similarly, an even bolder prediction came from Kobayashi and Masukawa when they looked at the 2x2 mixing of Cabibbo, of the light quarks. Even before we'd seen the charm quark, they realized that you needed a 3rd generation to allow for the observation of CP violation in the standard model. So here we have the usual CKM matrix, which describes the weak coupling between quarks amongst the 3 generations. And the fact that this is a 3x3 unitary matrix, and once you've done the rephasing of the quark fields, you are left over with one irreducible phase, which allows for all the CP violation that we see in weak hadronic decays. So this was, again, a remarkable prediction, again predicting particles at higher mass scales, this 3rd generation of particles which we had not yet seen, just from observations related to flavor physics. So, of course, there's many interesting puzzles in flavor, one of which is noted here is this very hierarchical nature of this magnitude of the elements in the CKM matrix. So it's almost diagonal, and as you move further away from the diagonal, you get smaller and smaller couplings. And unfortunately, the weak phase sits on one of the smallest couplings of all, so that overall the CP violation in weak hadron decays is quite small and can't explain the baryon-antibaryon asymmetry in the universe. However, it's still useful to probe CP violation, and I'll explain it a little more in a moment. And our principal tool for doing that is to reparameterize the CKM matrix in terms of one expansion parameter, lambda, which is the sign of theta Cabebo. And then you can rewrite the terms in terms of this lambda, another parameter a, and then these two parameters rho and eta, which are related to the imaginary parts. So this is what's giving us CP violation. So this parameterization is the Wolfenstein parameterization is due to him. So now you exploit the unitarity in this, and what that means is you can combine the elements of the CKM matrix, and because some of these are complex, you end up with essentially three complex numbers in the Argand diagram, and because of the unitarity, they must sum to zero. So that's really just can be visualized as a triangle in the Argand plane. And the important thing to note about this particular combination is if you look at the magnitude of each of these three terms, they're all of the order lambda cubed. So that means that they're all three sides are roughly of the same length, and hence you get non-trivial angles in the triangle, and it's the easiest one to make measurements of that are interesting to test the Kobayashi-Maskawa mechanism. And this, and you see here also, when you write this in terms of these elements, because it's in using the third column here, it's got the beauty quark in all of this. So all the sides and angles of the unitarity triangle can be measured in B decays. And an example here is this angle beta, which you can relate together just in terms of rho and eta. So we know this very well. This is the triumph of the initial B factories, which I won't talk a great deal about. But you can measure it in different ways. Essentially, you're just measuring two parameters here, but you can make a whole set of measurements. So each of these bands here corresponds to one type of measurements. And you can localize the apex of this triangle, essentially measure rho and eta. It's sort of renormalized in a little way that it's called eta bar and rho bar here. But what one sees is you can use different types of measurements to do this. One's at tree level, where you don't expect much contribution from beyond the standard model physics. However, you have loop level diagrams which actually give the most precise constraints from time-dependent CP violation, which I'll talk more about, and the mixing rate, and also there's still some contribution from CP violation in kaons. So what's interesting about this is because this is loop level, you can essentially explore potential new physics within these loops, and they actually constrain new physics up to very, very high mass scales by looking at this picture. So this is, again, the example of looking for beyond the standard model physics at very high mass scales, in fact, mass scales that are higher than those that can be reached directly at the LHC. So a goal of the next generation of B factories in LHCb is to make a comparable measurement in the tree level decays compared with the loop level, and of course improve these over time. I won't talk so much about the tree level measurements in this talk, but it's certainly one of the primary goals. So why we do this at the Upsilon 4s? So this is a bottomonium resonance, and it's the first one that's above the mass threshold to produce a pair of beauty mesons. So the 1s, 2s, and 3s are below threshold, and they don't decay to B hadrons. So here we just have the total hadronic cross-section as a function of the invariant mass, and you see the lower mass bottomonium resonances here, and this is the 4s, which is a small peak above the continuum background, which is just light quarks going to E plus E minus going to light quarks. But there is about a factor, this is about the cross-section from B mesons is around a quarter of the to light quarks. So it's a significant enhancement compared with elsewhere. So this is why we work at this point. Of course, we still have to worry about this background from light quarks. So there are advantages of doing this. One is these final states are very low multiplicity. You only have a pair of B mesons, you have nothing else. So this makes it very easy to reconstruct. And in fact, coupling that with the initial constrained kinematics from the electron-positron collision, we can make excellent measurements of missing energy. And I'll compare this to the LHC in a moment, but this is what we do very, very well. So we can reconstruct neutrals very well in this low multiplicity environment and missing momentum. Also, the B0 and B0 bar, because they're coming from this resonance, the epsilon 4s, which is a known CP state, they come out quantum entangled. So this means that while they're both still there, and they're in a quantum entangled state, so only when one decays do they oscillate freely, and this leads to very high tagging efficiency, which is important for time-dependent CP violation. And we also have a completely open trigger, as we essentially take 100% of all the BB bar events that are produced. There are, of course, disadvantages. There's a very well-known LHC experiment, LHCb, and also more and more CMS, particularly, and also a little bit Atlas, are contributing towards flavor physics. And that's because at the LHC in proton-proton collisions, there's an enormous cross-section for BB bar quark production. It's 5 orders of magnitude larger than the electron-positron. Further, they see all types of B mesons. We're restricted on B hadrons. Sorry, they have B baryons as well. We only have B0, B0 bar, B plus, B minus. And they also produce these with a very large boost in the laboratory frame because of the very high energies, and that allows for excellent time-dependent measurements because they fly longer distances, so that leads to better decay time resolution. So in our E plus E minus machines, we overcome this problem of the boost by having asymmetric beams. So the asymmetric beams that we have at Belle II and the earlier B factories allow us to boost the B0, B0 bar system and allow us to make time-dependent measurements and exploit that long lifetime of the B meson. So to talk a bit more about the detectors, there's a history here. Bell and Babar ran from so it's like 1999 for about 10 years, and they accumulated a data set just over 1 inverse Ataban and the epsilon 4s, and they made many contributions to flavor physics. Particularly, they showed that the Kobayashi-Maskawa mechanism was certainly the one that described CP violation in the standard model, and they for that Kobayashi-Maskawa won the Nobel Prize. But they also made observations of many new phenomena, semi-tauonic B decays, direct CP violation in B physics, and many others, particularly advances in electroweak penguins, for example. So the idea of Super-Keck B and Belle II is to collect a much larger data set than that was done by the first generation. So it's essentially to increase the statistical size of the sample. And to do that, we have to increase the instantaneous luminosity of the accelerator. And the goal is to do this by a factor of 30 as to what's been achieved by the first generation. So at the moment, we have a world record instantaneous luminosity of around 5 times 10 to the 34 inverse centimeter squared per second, but this is still a factor of 12 below the target luminosity. So I'll come back to this at the end, and this is the main goal that we have experimentally, is to try and increase this luminosity. But we have already accumulated a significant amount of data. It's almost as much as Babar ever did in our run 1. And we use this so-called off-resonance data to study the properties of the light quark E plus E minus to QQ bar. So the detectors I won't talk about a great deal. You see it's not perfectly symmetric about the vertical axis, and that's due to this asymmetry in the beams. So we have the higher energy electrons coming in from this side and the lower energy positrons. Everything is boosted forward, but it has all the good things that you need in a general purpose detector: silicon tracking for vertexing, large radius tracking for good momentum resolution, particle identification to separate pions from kaons primarily, homogeneous calorimeter, crystal calorimeter of cesium iodide, thallium doped, and then we have a muon catcher on the outside. So this just also shows the upgrade that took place between Belle and Belle II. We reused parts, particularly the very expensive calorimeter, and the return yoke for the solenoid, but virtually everything inside that was replaced otherwise. So I now want to talk about some highlights from the Belle II program. This is the vast majority of the talk. But first of all, I just want to explain how we make some of the measurements, because these things will come up a few times as I go through. So the advantage of E plus E minus is largely that you actually know what you're colliding together in the first instance, which is very different to the LHC, where you just have the parton distribution function and you know some gluons collided, but you don't know exactly what their momenta were in the initial state. So here we use the fact that we know exactly what the center of mass energy is, and it's very well known to a few MeV, to make particular kinematic variables. So one is the so-called beam-constrained mass, where we take our candidate B signal and work out its momentum, and then we use the beam energy to construct its invariant mass. Now, if it's a true B meson, it will peak strongly at the known B mass, and then anything that's combinatorial will just follow this smooth distribution with this kinematic endpoint coming from the beam energy. However, if you partially reconstruct a B meson, you lose a soft particle. That will also peak in this distribution, so you'll have a peaking background here. Or if you misidentify a pion as a kaon, so on and so forth, this will still peak in this MPC. So to separate this background, we also use the energy difference. So you work out the energy of the B from the B's full momentum, and then you subtract off the energy of one beam in the center of mass frame, and this should peak at 0 for a true candidate. Whereas if you miss a particle or you get the wrong mass hypothesis, it's offset. And again, the continuum follows a smooth distribution. So this is how we separate our signal from background, kinematically. We also have to worry about this continuum background, but because our B mesons are produced just above threshold in the center of mass frame, they have very little momentum themselves. So when they decay isotropically through 4 pi. Whereas when you produce QQ bar, they're jetty and they go out back to one another and they form collimated jets. So we exploit the shapes of the events in the center of mass frame to differentiate between them. So we don't just use one variable to do this, we combine many, and we exploit the power of machine learning, and we can distinguish the topologies by putting them into some multivariate algorithm which learns from simulation or sideband data how to distinguish signal from Monte Carlo. And then we often use the output of such a multivariate. So here is one from a boosted decision tree to separate signal from background. So the signal is here in pink, and the background is here peaking towards low values of this discriminant. And we can fit these distributions to help us extract the signal along with those kinematic distributions. So again, the B factory, because it's a low multiplicity environment, and we have these constrained kinematics, we also benefit greatly from the fact that we can fully reconstruct certain events. In particular, if you have a B meson that's decaying to a charm hadron and a number of pions on one side, you will learn the momentum of that B. And then on the other side, you can look for states which are quite exotic or rare. So here is a forbidden decay in the standard model, which is lepton flavor violating. And it's a kaon, a tau, and a mu. So you can just reconstruct the mu and the k, and you'll have a missing momentum vector for the tau, and you can just use the missing momentum to get a distribution and see if there's a peak there for the tau. And this is a very powerful way of discriminating background in very rare decays. So this is so-called full reconstruction or hadronic B tagging, and we use this for certain measurements. The downside is the efficiency is very low, so the big boost in luminosity that we hope we'll get will really benefit many of these searches. But a few of the results I show will use this technique. And of course, again, as with everything these days, we use machine learning to help us, so that there's machine learning on the tag side to get the best possible result. So moving to the bread and butter of our measurements, this is time-dependent CP violation. So how this works is that you have the B0, which can decay to some eigenstate, or it can mix and then decay to the same CP eigenstate. And in the mixing, they pick up one of the angles of the unitarity triangle, phi 1 or beta, and so there's a phase difference between these two paths. So there's interference, and hence you get some dependence on this phase. So what you need to do to make these measurements is to not only reconstruct your signal. So here I have the CP eigenstate. So these two leptons are coming from a J psi. So this is J psi K short. Then you have to tag the other B to know its flavor. So that's best done by using a lepton coming from semi-leptonic decay, but you can also use kaons and other properties of the event. And then this, because this depends on mixing, it also depends on the time between the two decays. It coherently evolves here, so your clock only starts when one of them decays. And then the remaining meson oscillates and then decays. So you need to know what it was at time here and here. So we use the tag for this, and we use the separation between the two vertices to get the time difference. And that's where we use the boost between the two beams. So this flavour tagging, again, is important. We use leptons, kaons, and we can look at the momentum of these other events in the event. And we've now used graph neural networks, which are more advanced multivariate algorithm, which better uses the correlations between the various observables that you see in the event. And we've actually improved our tagging efficiency by about 20% almost by using these new techniques. And we're now up to around 37%, which can be compared. This is almost an order of magnitude more than the tagging efficiencies at the LHC. Yeah, so this is just telling you whether it's a B0 or B0 bar, essentially. So it's a charge of the B quark, essentially. R is just quality, okay? So when you're down here at 0, it's tossing a coin to say whether it's a B0 or B0 bar. Here, you're pretty certain that it's a B0. Down here, it's a B0 bar. So, yeah. So, again, these analyses are done in bins of this QR, because obviously all the information lies in these two bins at the end. Stuff in the middle's more of a control than anything else. So the first of the measurements is a time-dependent CP violation measurement of B0 to 8 prime K short. This is interesting because it proceeds via a penguin diagram, so it's a loop, has access to beyond the standard model physics, potentially within the loop. And this can be compared to those B to J psi K short decays that happen at tree level. So if there's any new CP phase within this loop, it would show up here. And otherwise, it's exactly the same as what I described on the previous slide. And we've made a measurement using the full run 1 data. We have just over 800 events using 2 decay modes of the eta prime. And the eta prime, you see, involves photons in its final state. So that's excellent for Belle II compared with LHCb. This is a measurement that's difficult or almost impossible at LHCb. And we, again, do all those things I mentioned earlier. We use the delta E, the beam constrained mass, and the continuum suppression variable to separate the signal. And then we use the time-dependent information to get this distribution of the CPA symmetry as a function of this time difference between the two decays, delta T. And you see this oscillation, of which its amplitude is related to sine 2 phi 1. So the result agrees with that coming from the tree-level decays, but its precision, even with a smaller data set, is almost as good as the preceding measurements of this decay. So related now to the unitarity triangle, this isn't a time-dependent measurement because we don't have a vertex in this decay, but this is B0 to pi 0, pi 0. So if you look at our knowledge of the angles of the unitarity triangle, we now know beta and now gamma reasonably well. The one we don't know well is alpha, which is from this light blue sort of band here, is constrained. And how you constrain alpha is to use a combination of all the beta pi measurements and isospin to remove contaminating diagrams with penguins. This was proposed by Corona in London a long time ago. But the weakest link in doing this method is measuring this B0 to pi 0 decay. And that's the reason, is because it's got 2 neutral particles which are hard to reconstruct. But of course, at Belle II, we can do this. So a new analysis has come. Now this is a 4-dimensional fit, which is used, same as before, delta E, MBC, and some continuum suppression. But we also use this flavor tagging probability, or the wrong flavor tag in this case, which is all equivalent. And we can use the separation power on event by event level to get a better estimate of whether it's a B0 or B0 bar. And we're now making measurements that are as precise as those that preceded it. And by the final publication, we will have converted this to a constraint on alpha as well. So moving away from time-dependent CP violation, I will talk about our highlight result from the last year or so, which is K to nu bar. So this is an electroweak penguin. It can happen via these two diagrams in the standard model. It's third generation sensitive because it's involving neutrinos of all 3 generations. And it's relatively easy to predict in the standard model because there's no coupling between the initial and final state. You just have to worry about predicting the form factor of the transition of the B meson to the kaon. So there is an experimental challenge here. The branching fraction is small, and also with 2 neutrinos, you don't get any good kinematic constraint because you're losing two particles you cannot reconstruct in your event. So there's no peaking in kinematics at all. So we developed 2 methods to look at this. One is this traditional hadronic tagging, where you reconstruct fully a B on one side and then look for a single kaon on the other. And then an inclusive method was developed that exploits many features of the event, and again, machine learning, to extract the signal. So in particular, if you look at these topologies again, the B's are sort of isotropic, the QQ bar back to back. But when you have 2 neutrinos from one of the B's, you get something that's in between. You have this odd track, lots of missing energy, and then one isotropic B decay. And if you look at a event variable such as sphericity, which is telling you how isotropically distributed the tracks are, you have continuum events are piled up towards low values of sphericity, B events up towards larger values, and then in between the red is the signal for this K nu bar. So by combining many of these types of variables, we can actually distinguish between the signal and the background. And when I say many, I really mean many. There are actually 2 boosted decision trees used, one with 12 variables initially and then another with 35. The cascade increases the efficiency by a factor of 3. And then this is the classifier output in quartiles of the and quantiles of the efficiency. So this is the top 8%. So it would be uniform for signal and strongly falling for the background. And then you can fit this these distributions using templates to try and extract the signal. And there's one other variable used, which is the invariant mass of the neutrino pair, which you know reasonably well because of the constrained kinematics. The hadronic tag is much simpler. The additional energy in the calorimeter is a key observable here. So this is unfolding the bins in Q squared against those in this BDT variable. There are 12 bins that are fit with templates. And this is how the signal would behave, and this is how the background would behave. The signal, of course, is multiplied by a large factor compared with the standard model. We use these profile likelihood methods, which include all the nuisance parameters from systematics in the fit, and we try and extract the signal. But of course, using such methods, you have 2 concerns. One is whether your signal efficiency is correct. Is the boosted decision tree well modeled? Is it well trained? And have you understood if there are any sources of background that you may have missed that could fake your signal? So the efficiency validation is done by using a technique called embedding, where we take a high statistics type of B decay. Here it's again J psi to a charge kaon now for a B+. Then we remove the information from the B decay and substitute in the signal. But everything else is real data. And hence it looks like a large sample of the signal. And with this, you can test the efficiency and the performance of these boosted decision trees. So here are the outputs of these 2 boosted decision trees. The points are the embedded data, and the Monte Carlo is the histogram, and you see there's excellent agreement to around a few percent. So we feel we got the efficiency correct, at least to a few percent. The backgrounds are very thorny but again, we feel we're modeling things very well. This is a combination, a comparison of Monte Carlo and data, where you just take the kaon and look at combining it with any other oppositely charged particle in the event. And you see across most of the invariant mass range, you're having very good agreement between data and Monte Carlo. You see here the D peak, for example, and then there's the rho peak and other things down here. Sorry, that would be this is the rho, phi, so on, and this is just threshold here. So, we feel we're reproducing the data very well in Monte Carlo. And we also use sidebands, so instead of looking for a kaon, we look for a pion, and again, we see the background and the data agree with one another very, very well. And there are backgrounds from K-longs, which we don't reconstruct, but again, we could fake the neutrinos, but again, we feel we have all of this under control from detailed studies. So the final result here is for the inclusive tag, the red is the signal. So we see a clear B to K nu bar signal. And in the hadronic tag, which has lower statistics, again, there's some signal observed, but the uncertainties are much larger. So these are the two methods, and then we combine them together. So the combined result is that there's evidence for this decay, the first evidence for this decay at 3.5 standard deviations, and the branching fraction is significantly larger, almost by a factor of 4, than that predicted in the standard model, and there's a significant tension of nearly 3 standard deviations between the two. So we're following this up with many more measurements of B to K or K star nu bar. Work is underway. I can't say any more. Okay? Ask me in about 6 months. So K star tau tau was a more recent highlight. We presented this for the first time this year. This again, the third generation is the interesting part here. Many theories of beyond the standard model physics predict things going on in the third generation and not elsewhere. And it also correlates with other B anomalies. So semi-tauonic decays have been consistently high in their measurements at the B factories and LHCb. And this is the current, or not quite current, a few years ago, but it hasn't changed very much, from these ratios of semi-tauonic to light leptons. And there are certain theories that predict great enhancements of this particular decay, orders of magnitude enhancement, if you can explain these B to C tau nu transitions with certain models. I think this is lepto quarks, but I can't quite remember. But in the standard model alone, it's very, very rare, 10 to the minus 7. But we use this B tagging, so we fully reconstruct one B on one side, and then we look for 4 tracks on the other side, or also additional pi zeros to make rows. And we use all these different tau decays to make the efficiency larger, and we exploit the fact there's lots of missing energy because of the 2 neutrinos coming from the tau decay, 2 or 3, more than, sometimes there are 3 neutrinos, sometimes there are even 4. So we use this missing energy, and again, because it's fully reconstructed, there should be nothing else in our calorimeter, and these are 2 powerful variables to extract the signal. Again, I'm afraid we bundle everything into a multivariate because that gives us the best power, but it leads to sort of rather boring plots. But we've improved the limit over Belle by a factor 2. We don't see anything. You would have heard more about it if we had, but this is our fit to the run 1 data, and we're setting a limit that's twice as restrictive to any one that went before. So we're starting to get closer to the interesting region for this decay. So moving away from B physics in my last 10 minutes, I want to talk a bit about tau physics. So this, again, third generation, are very interesting. It's been widely studied in the past, and there are 185 different standard model decays of the tau if you look in the PDG. And this is, of course, very interesting for a lepton because you don't have any of this going on for electrons and muons. So it's a wonderful place to study the weak interaction. However, it's also a place where we may expect to see larger effects from new physics. So an example here is a tau to mu gamma transition, lepton flavor violating, which can happen in the standard model if an oscillation takes place within this penguin loop, which is extremely rare. So this is like at 10 to the minus 50. But many beyond the standard model theory suggest greater enhancements of this by many orders of magnitude. So to look for such decays and related decays such as tau to 3 mu, so you just imagine 2 muons coming off the photon here. And there are connections both to G-2 and to the B physics sector from these models, and to dark sector 2. So E plus E minus at the Upsilon 4s center of mass energy is an excellent place to do tau physics as well. So if you look at the cross sections here for different processes, you see the BB bar here is roughly 1.1 nanobarns. And then this slice in brown here is that to tau, so it's almost as large. So for every BB bar pair, we approximately get another pair of tau leptons as well. And we have this wonderfully clean environment with nothing else but the 2 taus to study them. So an example of how we've exploited this is to search for this tau to 3 muons. This should be accepted by JHEP now. So you look on one side for a tau going to 3 muons, which is a very distinctive signature. The other side you try and tag to make sure it's a tau-like event, not combinatorics. And again, we use a multivariate for the tagging on the tau side. And then we use 2 kinematic variables on the signal side to extract the signal, or the search for the signal. So there's the invariant mass of the 3 muons, and then the energy of the 3 muons less the beam energy creates a delta E-like variable. So this is this 2-dimensional distribution here. The boxy regions are the sidebands, which are used to do an empirical derivation of the amount of background we expect in the signal region, which is this sort of egg shape, which is oriented like this because there's a correlation between these 2 variables. So we estimate the background, which is expected to be around half an event. Unfortunately, we don't see anything, which you see from this projection. There's only 1 event within the signal region, but we set the world's best limit on this decay at around 2 times 10 to the minus 8, and this is reaching a level some models predict up to about 10 to the minus 9 or even higher for these types of decays. And this is an area of great competition. LHCb and CMS are in this 10 to the minus 8 region as well. So penultimate physics measurement I'll talk about is related to G-2. So a few years ago, there was a lot of excitement because the measurements of the muon G-2 were in disagreement with the theoretical prediction. And the theoretical prediction uncertainty is completely dominated by this so-called hadronic vacuum polarization, which is this higher order correction where you have a blob here, which is hadrons. And then they go back to a photon, and this alters the value of G-2. Now, since then, there's been lattice work which has moved the prediction much closer to the experiment. And then there was a measurement of the hadronic vacuum polarization inputs from the CM83 collaboration in Novosibirsk, which is again in agreement with the lattice and almost in agreement with the data. So this is very, very confusing. So what we need are more measurements to better estimate this hadronic vacuum polarization. So when I say measurements to work out this quantum correction, what I mean is that you can use the fact through dispersion relations that you can relate together that rate in the hadronic blob to E plus E minus to hadrons. Essentially, you're looking at the photon going to hadrons in the blob, and that can be directly related to the cross-section. And again, we normalize it by the cross-section to E plus E minus to mu mu. So this is this R ratio, and you have a kernel function from the QED. And what you see is there's a 1 over the center of mass energy. So the low center of mass energy stuff dominates this prediction for the hadronic vacuum polarization. So here, as a function of the center of mass, is the total hadronic cross-section with the various contributions. In yellow is pi pi, which is the dominant one. But in dark blue, the second largest one is 3 pions. And to the uncertainty on the prediction for the hadronic vacuum polarization, it's pi pi that dominates. But the next one at 15% is the 3 pions. Unfortunately, we don't have a pi pi measurement yet. We certainly are working on that, but we have done a 3 pion one. So for the 3 pion hadronic cross-section, we use what's called the ISR technique. So you reconstruct the 3 pions and an ISR photon. So you then scan a range of invariant mass. So what we then look for is essentially you have the 2 pions, 2 photons, and then you fit the 2 photon invariant mass to get the neutral pion piece. And that's what you see with the points here. There is a small background which is all constrained from sideband information. And this allows us to measure the cross-section, which you can then factor in to estimate its contribution to the hadronic vacuum polarization. So our measurement is here in the grey bands, and the earlier measurements are shown in yellow, orange, and blue from Babar and the Novosibirsk experiments. We're in slight tension with Babar, which is the most precise measurement in orange. We're about 2.6 standard deviations. Interestingly, our result pushes the value of the hadronic vacuum polarization closer to the measured value from the direct measurements at Fermilab. But of course, this is the precision here is limited because of our knowledge of the generator. This is higher order radiation and the pi zero detection, which is so these contribute such that we have about a 2% overall uncertainty on this measurement. But this is an interesting first contribution that we have to this program, and it's important to sort out what's going on with the G-2, as many of you know. So the last measurement, inspired yesterday by Murthy talking about the novel ideas Rajaji and others had in the 60s about non-conventional hadrons. There's, of course, been an explosion in the last 20 years of the number of hadrons. The number of particles discovered at the LHC is not 1, it is about 100 and something, with all the different spectroscopic states that have been found, particularly by LHCb. I'm not sure if it's quite 100, but it's very high now. So we've used our old Belle data to look at Upsilon 1s and 2s. So we took some data lower than the Upsilon 4s, and we will do that in the future at Belle II. And because these decays are OG suppressed to go to hadrons, already been observed that there's enhanced baryon production, which is lots of quarks in the final state. So maybe you can produce pentaquarks here. So we looked at inclusive production of J psi lambda, and then interrogated the J psi lambda invariant mass, and this is what you see here. And what you see is a peak at around 4.45 GeV. And this is consistent with a previous observation of a peak in a J psi lambda distribution coming from baryon decays at LHCb, B baryon decays. So we see evidence just over 3 standard deviations, and if we don't constrain our mass to that seen by LHCb, there's a 4 standard deviation local significance. So this is interesting because this is the first exotic state seen in the 1s, 2s decays, and also tell us something about what these exotic pentaquark states might be, given the different production mechanisms. All right, so to conclude, I should tell you about the future. And what I've been showing so far from Belle II, a little bit from Belle also, was taken between 2019 and 2022. And this is where we achieved our world record. This is the instantaneous luminosity here. And we had a long shutdown where we installed a new pixel detector. And there was also a lot of work on the accelerator to try and improve its efficiency and combat beam backgrounds. So we restarted earlier this year. Our instantaneous luminosity went up to what we had before almost, and the PXD2 was working well. Here I show the impact parameter resolution as a function of the transverse momentum of the track on a logarithmic scale. So if you have a hit in the closest layer in the pixel detector, you get better resolution. Second layer, you get slightly worse, and if you don't have any pixel hits, it's much worse. So this is really important for all our time-dependent measurements in the future. However, we're not getting up our luminosity to the level that we'd like. We want to be running it at 10 to the 35 and above, certainly in the short term. And there's a reason for this. We are having a lot of instabilities in the beam. Something called sudden beam loss happens. And this can lead to very large doses in the detector. Doses so large we quench some of the superconducting magnets. And this is hampering any increase in luminosity. And in fact, 2 of these losses damaged our new pixel detector. We lost 2% of the gates, or the pixels, because of this. So we've actually turned the pixel detector off as a precautionary measure at the moment. And a lot of the run 2, we haven't collected much data because it was largely for machine studies. And that's been good because we've understood a bit more about these losses. They seem to be related to dust in the beam pipe. So over the summer, we've done a lot of work to try and remove the dust. And also we've made gravity our friend by flipping over some bits of the beam pipe. I can tell you more about this if you're interested. And we'll start again in a few weeks and we'll see if this has improved beam stability and that we can move to 10 to the 35. So this hasn't been great news this year, but run 2 is long. We intend to run probably to the end of 2028 or later. So we still have several years. And if we can reach around 2 times 10 to the 35, we'll accumulate several inverse autobahns of data, far more data than any experiment previously. And then there's a lot of work going on for an upgrade program, which would allow us to get to this final luminosity of 6 times 10 to the 35. And this has a framework CDR now, which was released in June this year. So there's a long, bright future ahead going into the next decade. And hopefully, if you invite me back to the next TAP, I'll tell you more. So that's my conclusions. I think I'm almost out of time. So I've given you a brief tour of the flavour program at Belle II. And a little bit more. We're doing lots with the current data we have, and we hope we'll have results with instantaneous luminosity of 10 to the minus 35 inverse centimeter squared per second before too long. Okay, thank you very much.
Okay, now for questions. People who, yes, Indu.
The 3 pi, yeah. The next, you had the slide of the comparison between, before. That one, yeah, that one. Yeah, the sigma other by Bell. This comparison with Babar, they're not even, the orange lines are, at root smaller are above 0 and then that root. So it's not, is it calibration, is it?
So, yeah, so this is...
what happens at 0.784?
So the omega happens there.
Sorry?
The omega,
Ah.
I think, is there.
So some background subtraction?
So I missed several steps in this analysis. So background is unlikely to have much to do with it. So this is a logarithmic scale, so you're already down by 2 orders of magnitude on the background. And this dominant background that you see here, the yellow and the green, this we calibrate off data, so we're pretty confident we've got this right. Because you can make sidebands which have these data and we've got the rates right. What's tricky is the omega line shape and the unfolding that we do to get to this actual distribution of the cross-section in bins of the square root of S. And there's some suspicion that one or other of us is not necessarily doing the unfolding correctly. However, we've done many checks, so we're confident in what we've done.
Okay.
So,
No, at least yours is moving smoothly from below 0.78 to above.
but this is normalized to our results, so we're cheating a little bit here. So we make everyone else look bad, right? Because we're the ones sat here at. So this is relative to our result. So, and there's also issues potentially with the pi zero efficiency as you move along in invariant mass, because the pi zero momentum in these bins is different on average. So if there's some issue with low momentum pi zero reconstruction, which is not fully calibrated, this could lead to this kind of effect as well. Because this is very close to the 3 pion threshold, so your pion is very soft. It's being boosted to some momentum against the ISR photon, but again, this requires some further investigation. But we've done a lot. We're a live experiment, no one from Babar in this room, right? So they're doing this measurement, having been shut for nearly 15 years. So the level of scrutiny it gets compared with something from a live collaboration is significantly less. However, the people that do this are very, very good, so I don't know. No.
Thanks.
We have lots of members from Babar on Belle II, so we have good interchange. And in fact, the Orsay group that did this measurement, some of them are now members, so we can talk. So it's okay.
In addition to this PCS, there are these PC states that were also observed by LSCP. Is that possible to say something about them? There are 3 of them now.
Yeah. So there are ongoing searches. Now, the LHCb states, right? Some have been observed in baryons and some have been observed in B decays, right? Of the pentaquark states. So the problem that we have is statistics in the B decays. We will certainly look, but it's unlikely. These were fully hadronic final states, and we don't compete very well. Fully charged track final states, and it's hard for us to compete in terms of numbers. But we will look to see if we get some signal.
Sorry, Bell discovered also these 4630 and 4660Y states.
Yes.
Which were actually claimed as baryonium kind of levels by some theoretical studies, like baryon and antibaryon. Is there some efforts or some ideas to identify whether they are actually composed of baryonium kind of things or trimeson kind of systems or something like that? I don't know.
Yeah, so there will be an active program to measure the Y states. So these were studied largely in ISR events. So currently, because we don't have so much data, we haven't looked. But once we have more data, we will start using that sample to try and investigate all these different models of whether they're molecular, tetraquark, whatever you just said about the baryon system. Yeah, I'm no expert on the spectroscopy. I shouldn't have mentioned. I only mentioned it because Murti mentioned it yesterday. But no, but Belle II started all this renaissance. Bell started all this renaissance in spectroscopy by the X3872, and since then there's been this explosion of all these new states. So yeah, we know the baryon meson picture is no longer enough. But so where we will complement LHCb is we can do isospin states with pi zeros and neutral kaons. However, whether our statistics will be enough, we're not sure yet. Okay?
Maybe you said it, but on this thing, if you take your value of mu, how does it look with respect to G-2, the experimental?
Here, so if we take ours, it's a 10% shift. So here you're looking at whatever, 2.5 units. So it would move up to about here.
Oh, so it moves in the right...
It moves in the right direction.
Okay.
But pi dominates everything. So the current situation is you have this one measurement here, you have a Babar measurement around here, and you have 2 Chloe measurements here. And that's what's driving the position. And, yeah.
Can I ask one more?
Yeah.
So you showed P plus to K plus nu. Is B0 to K0 nu doable at all? Or
K0 to nu?
B0 to K0 nu.
Yes.
Is that doable? Is that already measured or no?
So exactly the same techniques can be used. You just substitute the charge kaon for a K short. Problem is you get at least a factor of 2 reduction because you don't have the K, you have the K short, K long. Then you get another 30% because you will look for the K short in pi plus, pi minus, and pi zero, pi zero. So the statistics are lower. So it'll take more data to see a significant signal, but it's certainly there. The mode that's of great interest is the K star nu bar, because that's a different spin as well. So if there's something, it's possible that there's a intermediate state there that's then leading to the nu bar. That would have different behavior given the different spin structure. So K star, K0, S, we even have a fully inclusive XS, nu bar. All these things are being looked at. But I can't say anything else.
The kinematics. So, thanks. The nu always comes in the same direction. The 2 nus are boosted in the same direction always.
No.
So that's, just that you had a little picture, that little cartoon had the neutrino always.
No.
No.
So, that's just how it was drawn. But in principle, you could have a zero
So you may have no missing energy at all if the kinematics is right,
No, you have
or no missing PT at least.
no missing momentum.
Momentum, yes.
Possible.
It's possible. Okay.
Because they could, well, not. Yeah, no, you'd have overall missing energy.
Yeah.
But not net missing momentum.
Correct. Yeah. Yeah.
So that's all included.
Okay.
I think in the back up. Sorry, I can
Okay, sure,
help
yeah.
you. This is the one I want. Okay, so this is the reconstructed invariant mass of the two neutrinos. Okay?
Okay.
So you see the signal is distributed in this way. This template is standard model distribution.
Okay.
So it goes down to very low invariant mass and can go up pretty much so that the kaon has very little. But our efficiency drops off because we need the kaon to identify the signal. So this corresponds to our efficiency is falling. But this is the distribution we have.
No, but what I was really thinking of was you can't tell whether you have 1 neutrino, 2 or 3, right?
No. Well, if you had one missing particle, that would be a peak in this distribution.
Of course, that's true. Yes.
Yeah, so we can tell 1 from 2, but we can't do 2 from 3.
Okay. Yeah, good. Thanks.
Okay, thank you. Okay. There are no further questions. Let's thank the JIP for fantastic talk.